Hello, it's Keith here, and this is lesson 9 of the so-called ChibiFighter assembly programming tutorials on the Z80. We're looking at the little ChibiFighter demo game again. We're going to be looking at the platform-specific code of the Amstrad CPC. Now, basically the way ChibiFighter does its graphics is it has a multi-platform module which I call MinTile, which handles the tile map and the sprite drawing. But this has a platform-specific module which is designed to draw one single strip of tiles across the screen, and then this is called repeatedly to draw a grid either for a sprite or for the entire screen. So we're going to be looking at that platform-specific code today. We're also going to be looking at the interrupt code which handles the sound driver. So we're going to be seeing that today, and this is really the, as I say, the only platform specific part of this game, because the vast majority of the code was multi-platform, and that was part of the thing that the MinTile routine was designed to do. So let's go over to our code and let's see what we've got. Okay, so here is the code. So we're looking at the CPC CF2 code today. Now, this is sort of a self-contained routine in the same way as the simple series was. So things like the base header, if you will, everything is really within this module. There's no call outs to included header ASMs or things like that. So this is a fairly self-contained routine. Obviously, there are lots of attached subroutines because including this as one entire ASM file would be a bit crazy. But it's not as split out as some of my previous examples have been. Things like the Grimes Z80, that had lots and lots of branch out code. I've not done that in this case. So we've got this do-di routine here, which is a macro with nothing in it. Now this is because on some systems I might need to disable interrupts when certain parts of the code are running, and this depends on how the interrupt handler is working. The interrupt handler I'm using today is a custom one and doesn't need the shadow registers and things, so we don't need to disable interrupts in those cases. But if the firmware was using those shadow registers, we might want to disable interrupts in some cases, which is why we've got that there. Got a palette definition here, which is the same as the ones I've used in the past. If you see other entries in the simple series, I've covered how that works in the past. Here we're installing our interrupt handler. We're using interrupt mode 1 here, and that means that we're putting a jump command at memory address 38 in hexadecimal. So the jump command is hexadecimal C3 here, and then we've got the address of the actual interrupt handler, and we're loading that into memory address 38 in hexadecimal there. And so that's what we're doing there. And then we're running the initialization routine for ChibiSound Pro, which is the sound driver that I've written for each system, and that's setting that sound driver up. Now, the interrupt handler itself, you can see at the bottom here. Now, on the Amstrad CPC, the interrupt happens 6 times during each screen refresh. So we don't actually want to update the sound that often. The music is designed to be played at 50 Hertz, and so that would be 6 times too fast. And so what we've got here is we've got a simple counter here. We've got song timer, which we load with a value of 6, and we decrease it each time until it gets to 0. And when it gets to 0, we update the sound. Now, if we were disabling and enabling interrupts, this is a bit more reliable than checking for the VBlank, because if we'd missed the VBlank interrupt entirely, we would end up with playing our sound far too slow. So this is a little bit more reliable, though a little bit more crude than checking the VBlank interrupt, which you can do via the CRTC parameters. But as I say, we're not doing that. Now, for the ChibiTracks play routine, which is the routine that updates the sound, we need to back up IX, HLD, EBC, and A and AF there, which we're using the AF shadow registers here, but the others we're just pushing onto the stack so that we aren't using those shadow registers and we don't need to disable interrupts anywhere else in our code. So that's all that you need. IY and the shadow BC, D, and HL aren't used by ChibiTracks, so relatively minimal sound driver there. And for ChibiTracks to work, we need ChibiSound Pro, the platform-specific sound driver, the tweener, which is used for calculating the frequencies, fraction 16, which is also for calculating the frequencies, and the main ChibiTracks routine there. And of course, we've got our binary files here for the song data. So that's what we've got there. So that's what we're doing for our sound. Now, how about the actual graphics? Now, the MinTile routine that we're using today allows for sprites to be horizontally flipped so that they can turn from one direction to the other, because it would be far too inefficient to have copies of all the sprites for both directions. It doesn't do vertical flipping this version, just horizontal. So now the way we do this quickly, because each byte of the CPC screen contains 4 pixels, calculating the flip of those 4 pixels would be too slow to do in real time. So what we're doing here is we're defining a lookup table, and what we're basically doing is we are going to have 256 entries in that lookup table, and each of those entries will contain the flipped bits for that byte. So at offset 1 of this lookup table will be the equivalent bit flip for the byte 1 horizontally flipped on this system. So what we're doing here is we're taking the bits for each of the pixels here, these 4 pixels here, and we're basically bit shifting these into the opposite position, and then we're storing that into memory address HL, where the L byte of the HL pair is the byte that's been flipped, and you'll see how we use that later. Now, for that reason, it's important that this lookup table is byte aligned. So basically that the first byte of this lookup table is at a 00 boundary. So it could be at memory address 8000, for example, 8100, but it can't be at memory address FFFE because it needs the bottom byte to be a 00 in that memory address there. So that's what we're doing there. That's being done by this align command. The align command is different depending on if we're using VASM or we're using WinApe. So that's why there's 2 versions there. So that is the lookup table and how we're filling it in. So we're filling it in with these calculations here. Now, we've got a get screen pos routine, which is used for calculating the VRAM destination. You can see here. We've got the various values here. The X and Y position are being converted. Now that is used to calculate the VRAM destination for the sprites that can be mid-screen, but the whole tile map itself was always filling the entire screen, so that would start from the very top corner. Now the do strip routine is designed to draw 1 strip of the tile map to the screen, and this is run repeatedly by the min tile routines. So when this is executed, basically BC will point to our tile map in the shadow registers. This is the actual tiles that we want to show to the screen, numbered tiles. Then we have the DE pair, which will point to the pattern data. This is the raw bitmap data that makes up those tiles. And then IYL is going to be the tile map width, and you can see we're basically using that as a count. Now the height of the tile map isn't within this code. As I say, that is being done by the min tile routine. Now we're going to be using stack misuse to transfer the bitmap data from the pattern to the screen. And so basically what we're going to do here is we're going to have a loop here, and we are going to repeatedly load in a tile number from BC, and we're going to check, and if that tile is 0, then we're not going to draw anything to the screen. We're simply going to skip this tile. The way we would do that is we would basically just increment the BC destination and move the screen destination across 1 tile, 1 8-pixel block across the screen. And we do that by incrementing the L part of the HL VRAM destination twice there. That misses 1 tile effectively. If the tile isn't blank, then we're going to draw it to the screen, and we're going to need to basically calculate how we're going to do that. Now we have a piece of self-modifying code here. What we're doing here is we're basically going to 0 the entry in the tile map so that it is a 0. The reason we do this is that the cache that does the background tile map is actually set to 0 once a tile has been written, and that's so it basically only stores the changes that need to be made to the screen and reduces the amount of total drawing needed. However, when we're doing sprites, the tile code is tricked into working as a sprite routine. Saves me programming by doing that, but we don't want to delete the tile map that is used to draw the sprites, because otherwise it will be gone forever. It's not a cache. And so basically this load BC, A here would be changed to a no op if we were doing the sprites by self-modifying code. But in this case, what you can see here is it zeroing the entry in the cache that was just loaded there. Now what we're going to do next is we are going to take that entry here, and we're going to effectively multiply it by 16, because there's 16 bytes for each bitmap pattern, and the reason for that is there's 2 bytes across for each 8-byte tile, and there's 8 lines. 8 times 2 is 16, so that is the offset within our DE pattern data that we want to use for our bitmap source, and we're then loading that into the stack pointer because we're going to use stack misuse here. Now stack misuse basically means that we're going to use the stack pointer to quickly read data from the source bitmap rather than using the stack for backing up registers and things. And so what we're doing here is backing up the real stack pointer, and we're disabling interrupts here. It is possible to have an interrupt handler that doesn't need you to disable interrupts, but it's quite complicated, and for this case it wasn't worth it. And this is a good reason why our interrupt handlers shouldn't use VBlank detection to know when to update the sound. Okay, So that's what we're doing here, and at this point our stack pointer is now this source bitmap data. Now what we're going to do here is we're going to back up the H part of our VRAM destination in B and also in the accumulator. Now the B part is being used to restore it once we've done the job here, and the A part is being used for the down line commands. Basically, when we want to move down a line, we want to add 8 to the H part of the HL VRAM destination. Now the way we're going to do that is we're going to add C to the accumulator, which has been preloaded with the H part of the HL pair, and the C register has been loaded with 8 here. This is all a bit weird, and I know it's a bit hard to read, but with a routine that's this frequently executed for this large area of the screen, I've tried to make every optimization I'm capable of doing so, and so you're doing an add 8 here is slower than an add C if I know that C is 8, and if I know the accumulator is already loaded with H, skipping that as well saves time. So what we're going to do here is we're popping 2 bytes, 1 line from the source bitmap here. We're loading the first byte to the VRAM destination HL, moving across the screen by inking L, loading the second byte to the screen. We're then adding C, which moves us down 1 line. We're then loading the DE pair, and we're writing them the opposite order around. So we're writing D and E this time, but we wrote E and D the previous time. And the reason we're doing this is we're basically making a zigzag across the tile. So we're doing the left pixel, then the right pixel, moving down a line, doing the right pixel, then the left pixel, moving down a line, and we're doing all 8 lines here. After each one, we're adding C, which is 8 to the H part of the HL pair, which moves us down 1 line on the Amstrad CPC screen. So we're doing that repeatedly for all of the lines of the screen. And then once we're done, we're resetting H back to its original value by loading it back from B, and we're inking L twice in the HL pair, and that moves us across 1 tile, 1 8-pixel block, and then we're repeating for the next tile. So that is how we are moving across the screen in that way. So there we go, that's what we're doing there, and that is enough to get us across the screen and doing an entire strip. Now, do strip reverse is a little bit different. We're going to need to use our lookup table, and we've got BC pointing to that lookup table. The initial code is basically the same, calculating the source bitmap in the pattern and loading that into the stack pointer. But when we pop DE, we're popping the 2 bytes from our source bitmap, but that is unflipped, and we need to flip that the other way round. So what we do to do this is we load in the C part of our BC lookup table with the byte we want to flip, in this case D, and then we load the byte from that table, which is the pre-flipped equivalent of that C value that we've loaded into our lookup table address here. And we're then writing that to the screen. We're then doing the same of moving across the screen by inking L. We're then loading the other byte into C and loading that byte's XFlip value and writing that back to the screen. We're then moving down 1 line by adding 8 to the H part. I had no spare registers this time, so I couldn't do the add C thing. So we're doing add 8 this time, which is less efficient, but that's all I could do. And we're doing this repeatedly again across the screen, flipping every single byte via that lookup table, which is what that BC thing is in all of those cases. And then we're just returning. So as I say, we're using the lookup table in this case to flip that data, and that is the best way of flipping the data on the Amstrad CPC that I know. And as I say, I'm not saying this is the most efficient way of flipping the tiles or doing the tile transfer. It's the most efficient way I am capable of programming. So as I always say, go to my website, download the source code and the build scripts. You're welcome to use anything in my examples you want, and if this is too complex for you, just take a look and maybe you can strip that tile code down and use it in your own programs, and make something simpler from it if you can. Now we're going to be going into the min tile code itself, which is multi-platform code, in a later tutorial after these tutorials have completed. So you've not seen all of the tile map drawing code today. That's by design, because we're going to go over that on a lot more systems than the ChibiFighter game supports, so I'm considering that a separate tutorial series. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.